And maybe we can start and join.
Okay, so you can start, Auriane. You have 45 minutes for your talk.
Okay.
Please shut off your microphone and maybe your video, except Auriane.
Ok. Merci, Monsieur le Président. Donc, chers membres du jury, chers connectés et chers clandestins, j'ai le plaisir de vous présenter aujourd'hui mes travaux de thèse intitulés « Mécanique numérique en grande transformation pilotée par les données, de la génération sur mesure de données à une stratégie adaptative de calcul multi-échelle ». Cette thèse s'est déroulée pendant 3 ans à l'École centrale de Nantes, au sein du laboratoire GEM, Institut de recherche en génie civil et mécanique, grâce à un financement de l'École doctorale Sciences pour l'ingénieur, à travers une allocation ministérielle. Elle a été encadrée par Laurence Ténier et Adrien Legge. Alors, la première partie de cette présentation se fera en français pour que tout le monde me comprenne et je passerai ensuite à l'anglais pour présenter le cœur de mon travail. Alors, comme toutes les thèses, le titre de ma thèse est assez long et peu accessible au public. Donc, j'ai choisi de commencer cette présentation en décortiquant mon sujet pour qu'on parte tous sur de bonnes bases. À la question « Elle porte sur quoi ta thèse ?» que ma petite sœur m'a souvent posée d'ailleurs. Je réponds souvent que je fais de la mécanique, et plus précisément de la mécanique des matériaux, qui consiste à étudier le mouvement et la déformation des solides sous l'influence de forces internes ou externes. Cette science permet typiquement de répondre à la question pourquoi Superman arrive à écraser la canette aux grandes dames de Batman. Un outil très utilisé pour répondre à cette question, c'est la simulation numérique, et notamment la méthode des éléments finis, qui consiste à découper les solides en petits carrés dont on peut facilement modéliser la réponse et donc avoir une idée de la réponse de la structure tout entière. Ma thèse s'est concentrée sur une classe de matériaux qui a la capacité de subir des très grandes déformations, comme par exemple le caoutchouc ou le costume d'Elastigirl qui doit pouvoir suivre ces très grands mouvements sans se déchirer ni se distendre définitivement. Et enfin, ma thèse s'inscrit dans une tendance récente de piloter la simulation numérique par les données, par la data, le big data. Donc ça, c'est un mot très à la mode aujourd'hui, mais qu'est-ce que ça veut dire en mécanique et qu'est-ce que ça veut dire de piloter la simulation par les données? Alors, les données en mécanique, c'est des quantités qui sont intrinsèques aux matériaux. En premier, on a la déformation. On définit la déformation comme un rapport de distance. Et puis, la contrainte, le stress, comme un rapport de force sur une surface. C'est les efforts internes aux matériaux. On peut avoir d'autres quantités qui sont pertinentes pour certaines classes de comportements, mais ma thèse s'est limitée à l'étude de comportements élastiques, donc des déformations qui sont réversibles et qui ne dépendent pas de l'histoire de chargement. Dans ces cas-là, les données en mécanique, c'est cette déformation et cette contrainte. Classiquement, ces données sont utilisées en mécanique numérique comme suit. Donc d'abord, on va les collecter à travers des essais expérimentaux, notamment des essais de traction, et on les met dans un graphe comme ça, déformation contrainte, c'est les petites étoiles bleues, c'est ça nos données. Sur ces données, on va venir ajuster une formule mathématique qu'on choisit au préalable, qui s'appelle le modèle de comportement. Et c'est ce modèle qu'on va utiliser dans les simulations éléments finis pour modéliser la réponse d'une structure. En post-traitement, on peut aussi collecter et regarder les données qui sont générées par la simulation numérique pour établir des critères ou avoir des informations sur la réponse de la structure. Dans tout ce processus, le modèle de comportement, c'est un concentrateur très puissant d'informations sur la réponse mécanique du matériau, mais on peut aussi le voir comme un goulet d'étranglement entre des données amont très riches et des données aval qui peuvent aussi être très riches. Une volonté récente est donc d'intégrer directement les données dans la simulation sans plus passer par ce modèle de comportement. Et c'est une idée qui a été introduite notamment en 2016 par Kirchdorfer et Ortiz dans leur publication Data Driven Computational Mechanics, que je vais appeler à partir de maintenant la DDCM, cette méthode particulière, la DDCM. Alors concrètement, comment ça marche la DDCM? Pour vous expliquer ça, je vais revenir un peu à un problème de base en mécanique. Donc sur la gauche, vous avez l'espace physique dans lequel une patatoïde va se déformer sous l'influence de déplacements et de forces imposées. Et puis sur la droite, j'ai mis les équations qui gouvernent ce problème. Donc, on a d'abord l'équilibre des efforts et la compatibilité en haut, avec les conditions limites qui leur sont associées en bas. Et au milieu, on a le modèle de comportement qui permet de fermer le problème. On peut regarder ces équations dans un graphe que je vais maintenant beaucoup utiliser, multidimensionnel, de la contrainte en fonction de la déformation en abscisse. Et on a classé ces équations en deux groupes. Le premier groupe, c'est le groupe E, comme équilibre en rouge, et qui est tracé comme une droite dans ce graphe. On a rassemblé les équations de la physique, qui décrivent vraiment la mécanique, au sens large, donc l'équilibre et la compatibilité, ainsi que les conditions limites qui lui sont associées. Et puis, le modèle de comportement, c'est la courbe verte que j'ai tracée également dans ce graphe. La solution du problème, c'est le triplet déplacement, déformation, contrainte qui vérifie toutes les équations. Et finalement, dans ce graphe, on peut le voir comme une intersection entre ces deux espaces. Comme je vous l'ai dit, le modèle de comportement, il est ajusté sur des données, donc, que je représente ici par des étoiles bleues. Et l'idée, c'est d'utiliser directement les étoiles bleues dans ce calcul. Donc là, qu'est-ce que j'ai changé sur la droite des équations? On n'a plus le modèle de comportement, je l'ai remplacé par une collection finie de couples déformation-contrainte. Et cette fois-ci, je l'ai appelé D, cet espace. C'est la base de données. Dans ces cas-là, l'intersection entre les deux courbes de tout à l'heure, elle est moins évidente puisqu'il y a une des deux courbes qui est devenue discrète. Donc on peut avoir plusieurs solutions. Comment on va résoudre ce problème? Ça va nécessiter de reformuler complètement le problème mécanique et je vais vous expliquer ça directement en éléments finis, dans une formulation élément fini. Donc sur la gauche, on a discrétisé la patatoïde en petit triangle, en élément fini, et sur la droite, j'ai reformulé les équations sous forme discrétisée. Pour résoudre le problème, on va associer à chaque élément dans la structure deux états. Un état mécanique, qui lui va vérifier les équations de la physique, et un état matériau, qui va venir sélectionner un couple déformation-contrainte dans la base de données. On va alors définir une distance entre ces deux états, qui sont associés au même élément dans la structure, qu'on va chercher à minimiser sur la totalité de la structure, sous contrainte que le point rouge, l'état mécanique, vérifie bien les équations de la physique. Le problème data-driven, ça consiste donc à reformuler la mécanique comme un problème de minimisation sous contrainte d'une distance bien choisie. Si je résume tout ce que je viens de dire, voici l'architecture d'une méthode de résolution classique en mécanique. On a trois entrées. La première, c'est les principes physiques, donc l'équilibre des efforts, la compatibilité des déformations. La deuxième entrée, c'est le modèle discret de la structure, son maillage, les conditions limites et les opérateurs qui sont nécessaires à faire les calculs. Et la troisième entrée, c'est la réponse du matériau qu'on modélise ici par un modèle mathématique, le modèle de comportement. Tout ça rentre dans une méthode de résolution qui consiste à résoudre des équations, un système d'équations algébriques linéaires ou non linéaires. Et en sortie, on a la réponse mécanique de la structure. Quand on passe à une formulation data-driven, on a ce genre d'architecture. Vous voyez qu'elle est quasiment inchangée. Les deux premières entrées sont exactement les mêmes. On a conservé les principes physiques et le modèle discret de la structure. Et on a remplacé le modèle de comportement par une base de données matériaux. La méthode de résolution data-driven, elle a alors deux sorties. Une réponse mécanique, qui vérifie les équations de la physique, et une réponse matériaux, qui est sélectionnée parmi la base de données qu'on avait en entrée. Et entre ces deux réponses, on a une distance que j'ai schématisée sur la droite. Les objectifs de ma thèse que je vais vous présenter aujourd'hui en trois parties, donc il y en a trois. Le premier, ça a été d'étendre cette approche aux grandes transformations, et donc pour ça, il nous faut fabriquer des méthodes de résolution robustes. Le deuxième objectif, ça a été de questionner ce qu'on doit mettre dans les bases de données pour que des simulations de ce genre soient fiables. Et donc, on va interroger comment générer des bases de données, qu'est-ce qu'on doit mettre dedans. Et puis, dans une dernière partie, j'ai regroupé ce que j'ai appelé des défis numériques qui ont consisté à s'attaquer à des problèmes complexes que je détaillerai plus tard. Donc, à partir de maintenant, je vais passer en anglais pour pouvoir présenter le cœur de mon travail aux membres du jury non francophones. Okay, I will start this presentation by showing you the work we did on finite strain finite element solvers for data-driven computational mechanics. The difficulty in finite strain is that you have two different configurations that are no longer indistinguishable. And this leads you to several strain-stress couple available, work conjugate strain-stress couple available. The first one, which I refer to Lagrangian, consists of the Green-Lagrange strain tensor and the second Euler-Kirchhoff stress tensor. And you can formulate the data-driven problem in this Lagrangian strain-stress space. The second one available is what I call the nominal formulation, where you use the deformation gradient tensor and the first Euler-Kirchhoff stress tensor. The first one was introduced by Nguyen and Kuip in 2018, but it only provided a specific example in 2D and on truss structures. The second one was introduced as an extension of the previous formulation in small strain in 2020 by Conti and co-authors, but it provided only a continuum mechanics formulation. So both of these formulations that I will address in this presentation need generic finite element solvers, which was one of the main part of my work. To explain you that, I will start with the Lagrangian formulation, the ES formulation. The principle is really the same as in small strain. You have a mechanical state, which verifies physical principles, and a material state, which is selected among points in the material database. Again, we define a distance between those two states, and we minimize the distance over the whole structure, keeping in mind that the mechanical state must satisfy the compatibility and equilibrium equations. The advantage of this formulation is that you have symmetric tensors, which reduces the dimensionality of the phase space, strain-stress space, sorry. But you have nonlinear constraints. You have a nonlinearity both in the compatibility and the equilibrium equation. As for the nominal formulation, the principle is again the same, except you changed this of strain-stress space. You define a distance between a nominal mechanical state and a nominal material state, and you minimize the distance over the whole structure with respect to physical constraints. The advantage of this formulation is that it is mathematically funded, but you work with non-symmetric tensors, which oblige you to enforce the conservation of angular momentum explicitly in the constraint set. Both of them, as I highlight in red and blue, rely on a double or are formulated as a double minimization problem. And this is difficult to address numerically. So we used an alternative minimization scheme, just as the one that was proposed in small strain originally. So I will detail this approach here. As input, as I said, you have the mesh and the database. Sorry, you initialize the material states first, selecting a point for each element in the structure from the database. And then you compute the mechanical states. You split the minimum in the minimization in two distinct minimizations. The first is computing the mechanical states, and the second one is the update of the material states. You repeat this procedure until you have convergence of the material states. And when you are satisfied, you can have as output the mechanical response and the material response. So this alternative minimization scheme can be viewed as alternative projections from the database to the constraint set and the other way around, as I illustrated on this graph on the right. And I forgot to mention that the letter Z stands for either the Lagrangian strain-stress couple or the nominal one. The computation of the mechanical state is the hardest part in this minimization. because you have a constrained continuous minimization with respect to nonlinear constraints. In each formulation, the nonlinearity is of different nature and lies at different places. So it required specific numerical tools for each of them. The first one is in the Lagrangian formulation, we used the original Lagrange multiplier methods, and we just merely consolidated the solution that was proposed before. But in the second one, the nominal formulation, we proposed an original solver dedicated to the mathematic formulation that was proposed using an augmented Lagrangian method. The discrete minimization to update the material states boils down to a local search for nearest neighbor for each element. So you see on the left, you have an element which is associated to a given material state selected from the material database. And it changes for each element. For this part, we used efficient tree-based algorithm, which reduces greatly the computation time. To summarize this part, we developed two finite element solvers dedicated to data-driven finite strain elasticity. The nominal one is mathematically funded, but it is more costly due to more complexity. And the Lagrangian one is more efficient, and it offers a lower dimensionality of the strain stress space. Both of them relies on the alternative minimization schemes for now. For the rest of the presentation, I will only focus on the Lagrangian formulation to present the remaining of the work we did. So with this, I move on to a second part of the presentation, in which I will show you the work we did on generating material database suitable for finite strain computations. In a previous experimental study, in a thesis that was conducted by Marie D'Alema and defended 1 year ago, we found that in experiments, even in the complex structure, only uniaxial tension was mainly represented in the structure. So the question was, what do you need to perform data-driven simulations? We decided in this work to explore this question only with artificial database to avoid the drawbacks of experimental data. First, we generated as rich as possible a database, I will explain how, which contains all possible modes of deformation. And we compare that with a specifically designed database resulting from a clustering analysis, which would simulate an experimental database. To compare these two families of databases, we use a test case in 2 dimensions, resulting from plane stress assumption and the compressibility of the material. We use the Lagrangian formulation, as I mentioned, on this structure, a perforated thin membrane with a perforated thin membrane. Okay, so in what is a Lagrangian database? It actually consists of the components of the strain and stress tensors. So you end up with a 6-dimensional strain stress space. And usually in the literature, to sample this space, we use a grid, a regular grid in strain space, and obtain the corresponding stress points with a constitutive model, which is later forgotten in the data-driven simulation. The problem of a grid in strain space it is that it is not efficient as was shown in the literature, but also it may not be physical. You may create non-physical points, which means that some points in the grid might not correspond to actual green Lagrange strain tensors. And in our particular case of 2D plane stress incompressibility, we need to sample the strain space with the incompressibility and force in the database. So we we formulate this with the stretched tensor for which the determinant must be 1. The solution to perform such a sampling, we used the method provided by Kunk and Fritzen in 2019, which consists in a linear dense sampling of the Lagrangian eigenstrains, which is the logarithm of u. I denoted y. And we wanted to have a mechanical control on this sampling method, so we also built upon the invariant basis introduced by Christiane and co-authors in 2000. And combining these two techniques, we performed what I called a dense and mechanically meaningful sampling of the stretched tensors. So it consists first on the top right as a linear decomposition of the eigenstrain on a basis of 3 basis tensors, which correspond to those modes of deformation. And then the sampling relies on a magnitude direction split strategy. So the first parameter to sample here is the magnitude of deformation, which is actually the invariant of the Yankee strain tensor Y, K2. And it also relies on a direction vector, A, which depends on the third invariant of the Yankee strain tensor, which gives you the mode of distortion. So its value, when it's equal to -1, it corresponds to equiaxial tension. When it's equal to 0, it corresponds to pure shear tension, sorry. And when it's 1, it corresponds to uniaxial tension. We also introduced a parameter theta, which we call the orientation angle of the principal strain occurring in the plane stress plane. The other parameters I will not detail today. Okay, so sampling the stretch space of the components of U with these techniques gives you a cone-like shape, like I show on this slide. I show also the influence of the parameters of the sampling method. On the left, the cone is generating with a K2 equals to 0.8, and on the right equals to 1. And you have the influence of the invariant K3, the mode of distortion on the left, and the influence of the orientation angle on the right. So you see that you no longer sample a cube or a grid in this space, but rather cones like this. The method relies on just a sampling then of this magnitude and this direction parameters. To generate several databases of this family, we performed a sampling which gave us from 200 to 25 million points in the database. And I show you some examples on the right. So you have on the left the 3D space spanned by the components of the strain tensor, and on the right, the components of the stress tensor. And here you have much more amplitudes than directions. Now you have much more directions than amplitude. And here you have an intermediate case. So this dense sampling methods offered us control on data coverage and mechanical relevance of the points in the database through 2 parameters, the magnitude of distortion, K2, and the mode and orientation of distortion through the parameters A, the direction. To compare with this very dense and as rich as possible database, we performed what we referred to importance sampling of the strain stress space to generate what we called DDI database. For DDI stands for data-driven identification. So it consists in generating data from a finite element simulation on a similar sample than what we use as a test case. You have here 2 holes. we perform several simulations on this structure and collect the reference strain-stress response in this multidimensional strain-stress graph. And we perform a clustering analysis on these points to obtain a material database. The material database is here illustrated in these 3D graphs of the strain and the stress components. And here we have control on data coverage and mechanical relevance of the points using a similar structure to the test case we want to simulate, and by prescribing various loading conditions. And we ended up here with only about 2,000 points. Okay, so I will now compare the results obtained with those two different databases. I will start by the actual goal of DDCM, which is to minimize a distance. So we will look at the final distances between the mechanical solution and the material database. I will plot this objection function as a function of the number of data points in the database. So here are the results for the two families. I also provide you with the results of the reference element, the finite element reference solution. You have the distance between the solution and the database. You see that they are very similar. And to discriminate the two families, I highlighted the corresponding points. You only have 1 point for the DDI database because we only generated one database. And on the right, you have the several dense databases. And you see that, as expected, the objective function decreases with increasing number of data points, which is logical. But we could see that this decrease is much higher with the number of amplitudes, of directions, than of magnitudes. To compare these two databases, in the next slide, I will compare the DDI database, so the important sampling resulting database, and the dense database with approximately the same number of points, about 2,000. And I will also show you some results of the richest database that we generated with 25 million points, which is on the furthest right. For instance, we can look at the global response of the structure. On the left, you have the DDI results and the dense results on the right. You see that the DDI performs already quite well with quite a few number of points, where the dense database is bad. The results are bad. But if you increase the number of points, you rapidly superimpose the response with the reference solution. And if you have 25 million points, you have a perfect superimposition. Okay. I will now present you a strain analysis that we conducted based on the parameters that are actually used to sample the dense databases, which are K2, K3, and theta. I will represent a point in the structure, the mechanical state of a point in the structure in this polar graph. So the color of the point corresponds to K3, which is the mode of distortion. The radial position of the point gives you the magnitude of distortion, and the angular position gives you the orientation angle. So we know that this particular point with this particular color and positions on the polar plot corresponds to a uniaxial tension of a specific straight ratio in this specific orientation. I now show you the results of the mechanical states obtained with the two different databases. On the left, you have the DDI database, and on the right, you have the dense database. So you see that you have the impression maybe that there are a lot of colors, a lot of different colors, which could trick you in thinking that there are a lot of modes of deformation in the structure. But if you see on the color bar on the top, I added an histogram, and you can see that there are much more purple point, violet point, which corresponds to uniaxial tension, which is consistent with the experimental observations. On the right, we'll increase the number of data points in the dense structure, in the thèse database, and you will see the cloud of points moving a bit. Okay, and here you have 25 million points. So you see that you have quite similar results between the two databases. But more instructive was to look at what was in the database in the first place, and what do you use out of these thousands or million points. On the left, I plotted the whole database on this polar graph for the DDI database, and on the right for the corresponding dense database with approximately the same number of points. And now I will show you the data points that were actually used in the simulation, which means that were actually selected at least once in the simulation. So you see that you are losing a part of the point, but you are losing much more points on the right, on the dense database, by a factor of 5, and only a factor of 1.7 on the left. And if I take the 25 million point database, I actually use only 1% of them. And you see that, again, the cloud of points are rather similar. Okay. So to summarize on this part, we managed to generate databases by having strong control on data coverage and mechanical relevance using 2 different techniques. And what came out of this is that the richness of the database is more a question of quality than quantity. You saw that if you have a very high number of points, you will actually use only those who are relevant to the structure. So in a sense, the importance sampling notion is superior to the dense sampling, because you may have similar results, but with much less points in the database. I will now present you what we can do to address complex problems in data-driven simulation. And we start with a more mechanical challenge, a 3D simulation, and a more materials challenge next to do multi-scale simulation. So first, our final objective was to perform a complex 3D simulation on this kind of T-shaped column rotating. We have a compressible material and obviously very large strain to simulate. So the challenges were to have a robust data-driven solver, which we covered in the first part of this presentation. And the second challenge is the high dimensionality of strain-stress space. Why? Because in 3 dimensions, you now have obviously 6 components for each of the strain and stress tensors. And you have then a 12-dimensional strain-stress space to sample or to fill with your database. Again, we used the dense sampling method introduced by Kuhnke and Français. Actually, it's the original one here. You have additional terms in the sampling method. You have to take into account the compressibility of the material by sampling the Jacobians, and the basis on which you decompose the Yankee strain is a larger one here. But the points are obtained as before. And to generate a database for this particular simulation, we sampled 50 Jacobians, around 50, around 100 magnitudes K2, and about 2,000 directions in the unit's hypersphere in 5 dimensions. So we ended up with a 10 million point database, which is actually not so dense, because filling the unit sphere in R5 with only 2,000 points is rather sparse. Okay, so this is the problem we want to address. And what we did was to perform 2 successive Lagrangian simulations. The first one used this original database with 10 million points. And the second one used a reduced database with only 75,000 points. Between the two of them, what we did was to select the data points that were actually used as material states in the first simulation. So here you have only 1 out of 1,000 points that are actually used in the simulation. Okay. So this is the kind of global response we can have for the structure. I plotted here on the deformed structure, the deformation gradient in the XY direction. You see you have very large strain. And I will plot as well the resultant force and resultant moments on the bottom surface, which is clamped. And I will plot this each component as a function of the rotation angle, the prescribed rotation angle theta. So I plot here the results for the first simulation with the 10 million points. The color indicates the component. And second, you have the results obtained from the reduced the simulation. You see that they are both very similar, even if you have only 75,000 points in the second one. And as an indicator, I give you the results from the finite element reference solution corresponding to this simulation with the same constitutive model. And you see that the results are very quite well predicted, except for the Z component of the resultant force at the maximum rotation angle. This can be explained by maybe two factors. The sparsity of the database that I mentioned already, and also that the alternative minimization is actually very suboptimal and maybe even more so in 3 dimensions. Okay, so to summarize on this part, we managed to perform the first successful, at least to our knowledge, 3D simulation in finite strain using data-driven computational mechanics technique. And we used this dense sampling method that was provided to sample the high-dimensional strain stress space. And we used as well a first DDCM simulation as a way to select the relevant data points in this huge database. So this is the feature I will use in the last presentation, in the last part of the presentation, where the objective is to perform multi-scale simulation. So at each material point in the microstructure, you have a microstructure of which you know the constitutive models and the behavior of the components, but you have trouble making a constitutive model for the whole composite. The available solution to tackle these kind of problems in the literature is on the one hand, to perform a lot microscopic computations, either to feed, train, or fit a microscopic model, or also, as was done recently by Xu and co-authors, to directly inject in a single-scale data-driven simulation. But we will focus on the other approach of multi-scale concurring methods, which consist in solving a finite element problem at both scales. So the F-square method consists in solving a macroscopic problem at each integration point of the macroscopic mesh. So as you see, you will have still a high computational cost because you have systematic evaluations, which are even increased by the additional evaluations of the microstructure that you may have to do to evaluate the tangent operator. And most of these evaluations may be redundant, actually. So the standard finite element F-square method has a direct link between the macroscale and the microscale. You have a systematic evaluation for obtaining the stress and the tangent operator. So we proposed to use DDCM solver as a filter between the two scales So the direct link between the macro and micro scale is broken, and the microscopic evaluations are only performed when necessary. To do that, we proposed a first idea, a prototype solver in small strain, which consists in starting from an initial database to compute a first mechanical response out of a first data-driven simulation. So I plot on the right the corresponding points. So the mechanical response is again the red dots, and the database is again the blue stars, with the macro strains in the macro strain stress space. And we decided to enrich the database only in regions where you are lacking data resolution, which can be measured by the distances between the mechanical and material states and their associated material states. Indeed, if this distance is large, you know that that you are missing points around this mechanical state. So we enriched the database based on a microscopic evaluations with the mechanical strain as input, as a boundary condition, and retrieving the corresponding stress from the microscopic boundary value problem. You repeat this procedure where the database is enriched on the fly until you are satisfied enough of the final distances between the mechanical and material states. The numerical example we did was on this same perforated membrane, and we started with a coarse mesh from a quasi-empty database of 0, strain stress state, and we performed the second one on a finer mesh where the database was resulting from this first simulation. I can illustrate here some of the results that we have. You have here the macro and micro Cauchy stress results in the XX direction. And you see that area of macroscopic compression correspond to area of microscopic compression, and the other way around. Our objective in using DDCM in this setting was to lower the number of evaluations of a standard Fe² method. So I have here plotted the number of microscopic evaluations as a function of the iterations in the macroscopic solver that you would use in the Fe² method. And you can see that quite rapidly the data-driven simulation, which is in a dotted line, outperforms the standard Fe². And for the finer mesh, we ended up with a database of about 50,000 points, which corresponds more or less to 80 points in each direction if you think of a grid. And this reduction is actually provided by the fact that we select only the relevant microscopic evaluations to be performed based on this distance minimization scheme. And I plotted here on the structure the number of microscopic evaluations in each integration point. So the colors correspond to a number, and a bluish color corresponds to very few microscopic evaluations. At certain points, you only had one. And the reddish color corresponds to the highest number, which do not increase, which do not go above 13. And you see that this is only in regions where you have strain and stress concentrations that you performed the most microscopic evaluations. So to summarize on this part, we provided a first idea of data-driven multiscale simulation where you no longer need a tangent operator or to evaluate it, and which relies on this notion of importance sampling, and you have no explicit microscopic modeling, which we found is a promising application of the DDCM. I'd like to conclude now this presentation. So in the first part, I showed you our work on elaborating 2 finite element solvers dedicated to finite strain elasticity. They both relied on alternative minimization scheme, and each of them has his advantage and drawbacks. We also performed an extensive study on material databases and especially on mechanical relevance and data coverage. And the thing to get out of it is that richness is a question of quality of points. And we also started to address complex problems, which both depended on data coverage in a specific way. The 3D simulation questions the high dimensionality of strain stress space, and in the multiscale simulation, we tried to propose an adaptive strategy to fill this strain stress space. Some perspectives to this work, I chose to organize them corresponding to the parts. The first one, obviously, maybe short term, is to improve solvers, because as I mentioned, the alternative minimization is suboptimal. We also would like to go towards tailored and adaptive experimental databases, which could use the mechanical analysis K2, K3, and theta to design experiments in order to enrich the database. And the first applications we did to complex problem maybe open more questions than provided answers, among them the ones that are listed here. Okay. With that, I thank you for your attention, and I'm now ready to answer your questions.
Thank you very much, Auriane. It was very clear in my opinion. So, Julien, you start with your questions.
Thank you, Mr. President. So, Ms. Auriane Platzer, so thank you very much for your presentation. I appreciate it a lot, this presentation. I think it was very clear, very pleasant to hear, very dynamic and lively, so thank you very much. I also like your manuscript, which I find very well written, and it included a lot of discussion, which I think will be very helpful for future studies. Even though it was a little bit dense, and sometimes it gave me a hard time to go into all the details, but I think it's a very nice piece of work. So I have some questions for you. So my first question, maybe it was asked to you many times, but would be what would be the main motivation for this kind of method as compared to, let's say, classical empirical construction of models from data?
I guess there are several answers to that questions, and maybe mine is, I mean, I'm not really in a position to say, you know, constitutive model is of no use. I mean, I have not enough experience in that. I would say that it's maybe until it's really, you know, standard and used widely, I think it's very interesting to think of what do you get, what can you get only from data, and with nothing else than the data. And I think you can already do quite interesting things, which obliged you to question the mechanical response and the adequacy to what you know of the material, maybe more than what you would do with a constitutive model, which you use maybe widely out of range that you use to fit this model. So I think in this aspect, at least, it's interesting. It's a new perspective on things. So just for this reason, maybe I think it's interesting to explore this idea.
So I agree with you that it can help developing new things. So it's very interesting. So it leads me to my second question. So this kind of techniques, so you construct everything based on the data. It means that you trust the data. So what happens if there are errors in the experimental measures? So how could you take this into account in this kind of algorithm?
First, in a way, you trust the data, but in a way you don't, because you actually have a distance to the material database. And if your data is sparse or very noisy, you will have a large distance to the database, and you will know that your data are maybe insufficient, maybe sparse, maybe noisy. But this finite distance is actually instructive on the quality of your data, I think. So you trust it, but you don't really trust it as much as you would do if you fit a constitutive model on it, where you no longer really care for the noise that was introduced and the bias that was introduced when you fit this. And the other answer is that I did not include in my work a study on the noise, and it was done in small strain, and especially to come up with maybe more robust solvers than the alternative minimization, which inevitably leads you to local minima, and which is a problem. I agree with you if you have very noisy data, and it should be done for a finite strain. But I haven't got the time to get into it and to really and also the interesting thing to do, but I did not do it either, is to really quantify the impact of errors on the mechanical response at the end once you've gone through the data-driven solver. I agree with you, it should be quantified.
Yeah, I think extensions to uncertainty quantification, aspects in this kind of approach would be a very exciting. So another question is, when you try to analyze the accuracy of your solution, I noticed somewhere that you said richness equal quality. So you are trying to construct, let's say, the most continuous database that you can. So why not trying to construct a kind of interpolation between points?
Well, that would be, I think, cheating with the technique, but also interpolating in the strain stress space in finite strain. I think it's not that evident. To be sure that the reconstructed points, at least the interpolation between two strain stress couple, is actually a strain stress couple. Yeah, in this particular phase space. So I think it should be explored very carefully. For instance, recently there has been some, let's say, enhancement of the data-driven solvers based on this local surface reconstruction or interpolation, and it has been done in small strain, but it should be maybe explored to see if it also fits a finite strain setting.
Okay. Now let's go to the multi-scale applications of your approach. One I think there was two very interesting ideas. What you do is that when you apply this to FE square, you don't have a tangent matrix, right?
No, you don't.
So can you explain me again why? Because how can you satisfy the global equilibrium in the structure?
Because I should probably go there. So it's in small strain, and So here you can replace all the strain stress couple with macroscopic strain stress. Okay. And no matter how you get the database, even if you get it in an off-light stage. So in fact, the advantage even in single-scale DDCM is that you do not care for the non-linearity of the material response. Even if the database is assembling a discrete sampling of what would be a nonlinear manifold, you don't see it in this setting. And there is no tangent operator here in the sense that I'm working in small strain. Maybe that's what got you confused. But there is.
So is it kind of fixed point algorithm instead
Yes.
of a tangent?
Yes.
Okay.
I mean, not to solve the equilibrium. The equilibrium is
but to solve the two-scale approach. So you have a kind of fixed point. You go to the small scale, go to the...
Yes. So no, the microscopic problem is solved in a separate stage, only when you enrich the database. And here I only solve a regular finite element problem on this microstructure, and I only add the strain stress point to the database. But you no longer have really concurrent finite element solving, which means you do not need the macroscopic tangent operator.
Okay. So
because
can
the equilibrium at the macroscopic scale is solved using only the regular DDCM setting, where it is imposed as a constraint. But you
say that it is only valid for small strains, right?
Yeah, because you could think that no, it's actually valid in finite strain. You no longer have this tangent operator in the sense of the differentiation between the macroscopic stress and the macroscopic strain. You no longer need that because you no longer need to model the tangent response of the material, of the macroscopic material.
Okay. I think the second very interesting point is that you can kind of generate the database on the fly.
Yes.
So I imagine that you don't really use the algorithm of the distance search, etc. Could you apply this to classical F square? I mean,
in a sense, that's what you do in F squared to generate the data that you need on the fly, but you just discard them as soon as you have generated them. So here the idea is to store them. I guess on the macro scale, you could use another approach which uses this data, which you store.
Okay. I was also wondering, so what were the additional costs related to the minimization and search algorithm in comparison with classical F square? So,
yeah.
So in classical F square, you have to solve the local nonlinear problem of the RVE. But my question is here, because of all the additional costs, is there a gain or?
I cannot really answer on the actual computation time because I have not performed the corresponding F square, the true F square, regular F square simulation. But the additional costs are actually quite low in data-driven because the computation of the mechanical states is just twice as large system as in regular F square at the macro scale. And the search for nearest neighbor is greatly reduced using the tree-based algorithm, which you can even improve, has been shown recently. So I would say it's still less costly because, to my opinion, at least, I think that the critical issue in F-square is really the number of finite element evaluations you do of the microscopic response. And I don't think that the additional costs that you mentioned would compete. I mean, would.
Okay, so maybe one last question, because I don't want to take all the time. So do you think, in your opinion, that there are hopes to extend this to internal variable problem?
It's been there are people working on that very hard. That's for sure. And I think again, maybe here the discussion on what is material data, what do you have to take into account, is even richer, because there are been methods to take into account the whole history, the past strain, the past stress, or using somehow internal variables. So I think there is more than hope. It's ongoing work, and well, I think my work is maybe a first step towards finite strain history dependent behavior.
Okay, so thank you very much. So in any case, my remarks were not critics, just because it's very interesting. So thank you again for the discussion, and Mr. President, I'll pass.
Thank you, Professor Yvonnet from University Gustave Eiffel. Now I give the floor to Professor Kepp from Stuttgart University.
Thank you very much, Mr. President. I hope you can hear me clearly.
Yes, that's perfect.
All right, perfect, yeah. Also, many thanks to you, Ms. Platzer, for this very impressive talk, I have to say, and even more impressive PhD thesis that you have written. I was overwhelmed by that in a certain way, not because only of its, say, massive length, but also because of its amazing depth, surely, and because of all the care that you have spent in writing it. That is totally clear. And that's also that also applies pretty much to the talks that you have presented today. So thanks a lot.
Thank you.
Perhaps just a couple of questions that also go into the direction of what Julien already asked, perhaps. However, I would like to start with a very general question, and that is also directed towards the motivation of what you are currently doing or what you have done in your PhD thesis. And because you opted for replacing something that we took for granted for such a long time. Yeah, so all of us, maybe as continuum mechanicians, say what you have at hand always is something like a balance law and so on, kinematic relations, boundary conditions, and a material law. Now you say, okay, let's get rid of it. And could you just let me know, because one of the main motivations is, and I also understand that motivation for sure, that we lose a lot of information by replacing this wealth of data that we have at hand by just one function that is basically doing an error everywhere. Yeah, because maybe you don't match a single point of your measurements, but in average you are perfect. Né? Now I come to the question, and that is, do you also lose information from your point of view by just taking the data and by missing? Or do you miss somehow the law? You get what I mean?
Yes, I do. Tricky question.
Is there some kind of insight from your perspective?
What's sure is you no longer have this interpolation, extrapolation perks of the constitutive model. So you may have to deal with insufficient data in terms also of range. I mean, if you don't have it, you don't have it. Mm-hmm. So you maybe in this perspective you lose something by not using the constitutive model, but at least you're sure that what you're using is only what's available, in that you didn't extrapolate it or model it. But is there hidden loss, you would say? That's your question.
Yeah, maybe some insight into the behavior of materials. So to be honest, I came across this question when we were trying to publish our first paper in this, and there was this question asked by a reviewer. And he made the point that usually when we are dealing with, let's say, material laws, and you have something like a free energy function, then you can make sure that that you will fulfill the second law of thermodynamics all the time.
Yeah.
That's one way of showing it precisely. And now, if you don't have an energy, do you run into problems with that? Would you say so? Because it's clear that one can say, well, the data is the data for sure. It's
yes, I understand. I have to say I don't really know how to answer that. I'm not a specialist of thermodynamics, and
yeah,
I don't know if you can have the same reasoning to show that that everything is falling into places, into the right place.
No worries. I mean, it's. I think it's also a tough question. Maybe also a tough question to start with, but it went also in a similar direction as what Professor Yvonne currently asked. Because how do you want to include something like internal variables, of which we precisely know how to deal with them, when we have a model, yeah, to have all the physics basically in charge. But that's totally fine. Maybe another question is also, I think you mentioned already that perhaps you can actually not say something precise about that. But since we also did some work with Fe square and homogenization, I was very much interested in the last chapter that you have provided, and also the discussion of today with the data-driven Fe square. And I think one particular charm is that you can basically on the fly compute material data that you need at the macroscopic scale. And in an Fe square approach, you per definition don't have a free energy. So it matches, it fits perfectly. So congratulations for doing this. And I think another wonderful benefit is that you get rid of this effective tangent moduli that you just don't have to compute. Now the bottom line is, now at the end of the day, when we do these computations, we want to be as fast as possible with what we do, because one of the main drawbacks of Fe square is that it takes enormous amounts of time. Maybe I just ask the same question again, but could you estimate if you are quicker? Because one of your headlines in this talk was accelerating Fe square. So that would be great if you could accelerate it.
Yes. I only focus here on the number of evaluations, which I think is really the critical point. But also maybe another insight of this is that the first simulation, if you start from zero, you would have to compute. I will go there to generate a lot of points on the fly, and so to enter this loop that you proposed in the solver a lot of time. And then you'd have a great maybe a large computation time. But as you store the data from maybe one simulation to the other, once you've had a rich enough database, you no longer need to generate that much point on the fly. So you drastically reduce the number of microscopic evaluations, and the one data-driven simulation, one single data-driven simulation, can be very, very fast, and maybe not truly compete with a standard finite element simulation at a single scale. But you usually converge the data-driven setting with within 10 iterations or something. So I mean, it depends on the the number of database of the number of points in your database, but you can have a quite satisfying result already within quite a few iterations. So, but I totally agree with you and Professor Yvonne that we should perform the corresponding F-square method to really see where you're losing time and if you do accelerate them.
Yeah, I totally agree. So this would be very, very, I think, valuable information
sure.
To truly see that. And yeah, maybe if you are quicker, I mean, that's one major argument then also for this method. Because in fact, when also just from my own experience, when we are dealing with these things, somehow still some problems also always remain. And one is with regard to the computation time. So how is your experience there? Could you perhaps once more comment on that? Because we figured out as soon as you go to, for example, 2 dimensions, and we never went further, only up to 2, everything takes a long time for us.
In data-driven, you mean, or F-square?
No, it is, let's say, standard. Let's say the standard 1-scale approach, nonlinear elasticity, 2D Lagrangian formulation as you have proposed.
I haven't much experience in small strain. I quite rapidly took it to finite strain, but
no, I mean finite strains.
Yeah, okay, finite strains. Yeah, I don't really remember the computation time I gave. It takes forever if you have a very bad database. That was the case in my dissertation with the standard experiments with the database, which only consists. So it takes forever there. And if you have a better suited database, you have. I do not really remember.
Did I overread it in your thesis?
About 1 hour? No, several hours. Yes, it's in hours. I think I really do not remember. Oh, wait, where is it?
Doesn't have to be a precise number, no?
Yes,
but for us it was a large integer value.
Collect the numbers. Yes, it really could take hours. I agree with you, but I really I didn't really mention much computational time in my dissertation and even today, because I have to say I have a very engineer code which only gets things working, but not really optimized at all. What I did was more finding algorithm than solvers actually, and so I don't think my computation time are really relevant, but sure, it takes far much time, at least for now, than a regular finite element simulation with a constitutive model. That's for sure.
Yeah, I think, but it's also not problematic. I mean, these are things that are under development. I mean, it's still on the way.
And it can be accelerated. And once I really had at the beginning, it takes forever if you use a linear search algorithm. That's for sure. But once you use even this very simple tree-based algorithm, which is ready to go for in MATLAB or Python, even in there you get much time. And if I had better solvers for linear systems, I would be quicker. I haven't looked much into that.
Okay, no, that's great. Yeah, I'm looking at the watch. Perhaps you allow me one last question, and that is when you look at the FE² perhaps once again, and maybe I merged 2 questions, because one major thing is always the computation time that somehow bothers me when doing these things. The other thing that sometimes I wonder about is what's with the data, in fact, because you have now pursued a way in which you have generated the data in silico, so artificial data set from energies, in fact.
Yeah.
And that's also what we did. And now what you have is in the FE², you generate the data set on the fly from microstructures.
Mm-hmm.
And then the microstructures in turn, again, have the energies,
Mm-hmm.
right? So at a certain point, there are energies. Could you also imagine to do that in a full data-driven scenario? Would that give you any advantages? Just to perhaps have the data sets at every scale available?
Mm-hmm. Yes, I think you could do. I mean, nothing prevents you from doing a full data-driven at both scales. The idea here was to have something in a reasonable amount of time, and also because maybe one could think that, you know, linear elastic model for I don't know, glass fibers is probably good enough. So you can imagine that you can rely on it, and also rely on any constitutive model of the matrix for, let's say, simple microstructures. And maybe you don't have to go into the effort of doing something data-driven, which can double your problem of having a satisfying database. So that's why we went with this first approach here. But of course, you could imagine doing a full data-driven at both scales.
Very interesting. Yeah. Thank you very much.
Thank you very much.
I think then I would hand over again to the president. Thanks, Ms. Platzer.
Thank you.
Thank you, Professor Kepp. Now I give the floor to Professor Stéphanie Ries from University of Haarlem.
We can't hear you. You're still up.
Yes.
Thank you very much, Mr.
It's
President.
better now.
And I also would like to congratulate you, Auriane, for this really great work. I'm really impressed, first of all, by the thesis, 300 pages, really nicely written, and then your really very nice talk. I mean, this was also really a highlight. So, but certainly I also have some questions. And the first one is probably also a little difficult, but I remember that we talked about that a little at the Blackboard in Aachen, so
yes.
You might be prepared already. So you call as also at the end the formulation PF mathematically founded, and you say about SE more efficient. This was towards the end. Or you said that where was it? That SE is an engineering approach and nominal formulation mathematical approach. Yes, I'm a little, let me say, do not agree really with that. And so I would like to ask you why you say that the nominal approach is the mathematical founded one, because I mean S and E is a very good idea in my opinion, as you also show them.
Yeah, I also think so. It was not my intention to, you know, frustrate anyone. It was more to say that actually the nominal formulation was, at least for now, introduced in a really mathematic paper. I mean, it's from a very, it's math. I mean, and that in this paper there is proof that the data-driven solution converges to the reference one when you have a continuous database. And this effort has not been done for the ES formulation, so it probably, maybe it is. I mean, I think Michael will have something to say about that, but I call it engineer solution because it works. We haven't found anything that makes it fail until now. And but there is a grounded math proofs that the FNP formulation works. But it's in the perspective, it's of an infinite database, continuous one, which is not what you have in real life in a real simulation. So that's why I make this distinction. But
yeah, I think
it doesn't mean that ENS is not a good idea or not founded.
Yeah, I mean, we have a lot of mathematical works also in continuum mechanics. I mean, very early works
Yeah, sure.
in the 60s already, which deal with material objectivity, for instance.
Right. Yeah, sure.
And therefore, I would have definitely expected that you should use the pairs E and S, because F still includes the rotation, which you usually do not put into the constitutive law. But I had a question concerning the slide, which you just showed. Can you go back quickly to, you had also Cauchy, and then you mentioned the D. I mean, the Eulerian formulation.
Yes.
Maybe I also ask about that. So did you try this out actually? And what is the D in your case? I mean,
maybe it's not really, it's not very rigorous on this slide, because the D here is the deformation rate.
Okay, so the deformation rate, yeah. I assume
conjugate strength space, but so I haven't tried the Eulerian framework, which was actually used for the data-driven identification formulation in finite strain by Marie D'Alema, using not D but logarithm of and I just didn't do it out of well, I started with the publication actually of Professor Kuip as a starting for my PhD, and then there was not much time to explore the Eulerian framework, but which I would say from a numerical point of view is maybe trickier, because you have to update the deform mesh every time. Where when you are in the Lagrangian framework, you can pre-compute everything. So, but I guess it's out of who prefers what when they are coding finite element solvers.
Marc-André Kuip pointed you also already to this question, whether you consider the physics in a correct way, or let me say, you cannot be sure that you consider it if you take only data. There are very famous things to consider. For instance, material objectivity. This is clear. Therefore, SNE is, in my opinion, very clear. But you could also include additional things. For instance, if you know that your material is purely or more or less isotropic, you could implement material symmetry in a good way. And in this way, you could reduce the amount of data quite significantly, in my opinion.
Yeah, that's one direction we haven't really explored it, but maybe I would precise things on the fact that someone left. Okay. Sorry, the solution that you get out of the data-driven setting is always the mechanical solution, which lies on the physical principles which you enforce. So you know that all the time, even if you are far from the material response, you have a mechanical solution which is balanced and compatible. So maybe that's one.
Yeah, this is the balance equations which you fulfill. But when you set up the continuum mechanical material law, I mean, this is very old knowledge that you can obey certain principles, fundamental principles like material objectivity is a good example, but also certain material symmetries, or you could also look at equipresence, homogeneity, I don't know, there are many things already available in the quite early literature, and it would be interesting to put this knowledge into the data, because then you would kind of obey these principles in a, let me say, in a simple way. This was the point. Therefore, I was also a little wondering about this discussion about the strain. Could you go to that maybe? This was also on a page a little further than that. You introduced the green Lagrange strain, and then you said something like determinant of F larger than 0, I think.
Yes.
This was,
yes.
Yeah, here, thanks. Maybe this is the, why do you say not physical? I mean, usually, certainly determinant of F has to be larger than 0. Is it now the argument that you want to exclude here double points practically, which come out due to the rotation, which is still included, or what is the argument here? I simply did not understand it.
The argument is that if you sample on this grid in the components of the strain tensor, you may have points in the grid which do not fulfill this equation, which I could have written also using the compatibility equation. So it's just to say that when you sample the strain space with a grid like this, you have points in the grids which are not really strain tensors. Actually, they're just symmetrical tensors, but they are not strain tensors.
Yeah. Okay. Now I see.
Maybe not very, influential in the simulation, because you would guess you would never use these points. So it's not that bad, maybe, but it was just.
Yeah, you're right. Yeah, sure. And it's simply a little misleading on the transparency, because it would be good if determinant of f is larger than 0. Clear. This is more clear now. Another question. I think somewhere in between, I think it was on page 20, you talked about, I think you mentioned incompressibility, right? It is written there. So first of all, incompressible material means that you also put this into your artificial data generation, probably. And do you observe that the algorithm behaves, or that the iteration is more difficult in this case if you have incompressible material?
No, that may be an advantage of the data-driven setting here, is that you do not see, the algorithm doesn't know that there are incompressibility somewhere.
Yeah, okay.
It's only encoded in the data. So the simulation is not harder to make as it would be in finite element simulation, where you would, but it is a very specific problem here, because you are in plane stress. So even in a regular finite element simulation, you would have everything under control, let's say. So, yeah. But it would be interesting to compare that for a 3D problem, for example.
Yeah, exactly. Yeah, very interesting. Yeah. I think the question about the CPU times was already asked. Can you maybe go to 37, page 37? Yeah, Marc-André also asked that, but I don't know in which context. Here you have a very interesting comparison between different choices. So the finite element solution was done in a different code, I assume.
Yes.
Okay. So you have trouble to compare simply the CPU times. I assume.
Yes.
Or if you put everything in the same code, and even if the code is not so good,
the codes are very similar. So yeah. I would be able to compare that, but unfortunately I don't have that in mind. So
maybe
I can answer you.
Maybe qualitatively, have you some idea how long it takes? If you compare it.
The finite element simulation have a. Excuse me a second.
If you don't, it's.
The finite element simulation is. It also depends on the number of time steps, which was not really optimized here. And I think it was less than an hour with my code, and with the data-driven simulation, it also takes within hours, but not much. Not.
Okay, so
and the idea also in my whole work was to perform everything on my laptop. Sorry, so I haven't. Everything is less than a day anyway.
Yeah, right.
For sure.
Another question. I think you introduced. This goes back to my first question. So you know exactly that the second Piola-Kirchhoff stress is symmetric.
Yes.
And I think you introduced this this requirement that PT f to the minus t has to be equal to f to the -1p. Now you introduced this by means of a Lagrange, augmented Lagrange formulation.
Yes.
Did I understand it correctly?
Yes, that's it.
Yeah, here, exactly.
Yes, I enforced the last constraint in the augmented Lagrangian formulation.
So this is actually an additional equation then, which you have to consider, no?
Yes, sure. And that's what makes it all difficult. At the beginning, we did not consider it, and so you would have only the problem of dimensionality. But with this additional constraint, and we haven't found, at least yet, a way to really bypass it.
Yeah, sure.
We can't, and so obviously it's an additional constraint which increases the size of the system you must solve.
Yeah, it's clear. Therefore, and then I would like, last question now, and don't want to take so much time, maybe the page 43. I mean, I think that this is really a very interesting and important result. So you make something like hyperreduction. I mean, our president, David Rickel. Yes.
Yes.
And this is really nice. I have to admit that I do not completely understand the figure here on the left side. I mean, so it's clear for standard FE2, clearly the more microstructure evaluations you take, the more iterations maybe until macroscopic equilibrium. But can you explain again maybe why this is such a good situation for the DD? I mean, this is an important result, but I have trouble really to get this curve here.
I think a large part of the reduction is due to that you don't have to perform additional evaluations of the microstructure to evaluate the elastic tangent moduli. So that's one part of the reduction. And the other part is that you no longer perform systematic evaluations at every integration point.
Yeah, this is clear. Yeah.
So
this is the point. Okay, I thought because you write.
But why does it? I mean, perform so well? You mean?
I was not completely sure what you mean also here by which iteration you mean here. So is it here the Newton iteration until?
Yes, it is. Yes, it's the Newton iteration you would use in a standard F square for the macroscopic problem.
Yeah. Thanks. Really very interesting.
Thank you.
Thank you very much, Professor Ries. And now I leave the floor to Piotr Betkov, docteur ingénieur habilité from University of Compiègne and CNRS.
Yeah, so thank you, David, for this nice introduction. So thank you, Auriane, for this very nice presentation. The pinnacle of the 3 years process. We had already the opportunity to meet several times, so I could ask already some questions. And I would really join with other persons with a comment about the quality of your manuscript, which I think it could be serve as a reference text in the domain somehow, because I have particularly appreciated the way you introduce the things in corresponding degrees of difficulty with it. So I basically have 2 questions. So the first question is something that Julien has already asked, and there were some also elements in the questions from Stephanie. It is about interpolation, and you have answered, of course, that it will be a little bit dangerous because you possibly would not recover mechanical properties. And then with the remark by Stephanie, when she said, okay, but do you take into account symmetry, some additional assumptions, something that you know? And where comes my question is not really this precisely, but it is the intrinsic dimensionality of your databases. Because if you have your 6 in 3D interpolations, and you have nonlinear process. So you basically would represent clouds of points. Yes? But these clouds of points correspond to subsequent mechanical states, to different trajectories. You cannot go from any point to any other point. Not all jumps are possible, possibly. It depends on your experiment.
Yeah, well, I mean, if you will, in elasticity, in theory you can, but yeah, sure, you would have generated them from experiments in a certain history.
You are constrained by your experiment, whether it is a numerical experiment or an actual experiment. Anyway, you will not explore all the states. So that is the question: what is the right coordinate system? It is maybe not exactly strain, stress, 6 components, but it could be some generalized coordinates in which you will significantly decrease the dimensionality of, you can, for instance, as we do in principal component analysis, if we have put all the trajectories somewhere, we could possibly recover something that is governed by a lower number of modes. And maybe what is your opinion about doing this kind of job and then using this mode to perform actual physical experiments to get the databases corresponding to what you want to get? What do you think about this?
You would need to perform some kind of model reduction, for example, principal component analysis on the data first, and use the reduced coordinates in the data-driven simulation, or use
interpolate the reduced coordinate, then come back to the full dimension in order to recover the stress states. Yeah. So you don't necessarily need interpolating. You can just do model. You can just do principal component analysis just on your discrete data, and then recover the modes that you can use as input to your simulations. So it means that you will have on one hand this mode, numerical simulation, and then you could get an experiment to shift what you get from numerics to make some correction with respect to the experiment. You see?
Okay.
Because your simulation, if you use simulated data, okay, so you have let's say modeling error, and then if you manage to recover some fundamental behavior from this numerical behavior, then you can possibly perform a lower number of experiments to shift the kind of manifolds that you obtain. It can be a discrete one, you don't need to have a continuous one, and to shift it and to stick better to the experiment.
Yes, you can probably analyze the database to precisely know which experiments you would need to enrich it.
The idea is to get a lower number.
Yeah.
We're not able to perform as many experiments as we.
Yes, sure. That I think that's that was the goal, trying to define indicators, and in a sense, this K2, K3, theta parameters are some kind of reduced coordinates of describing which type of experiments you would need to do to enrich and you would only need this particular modes and magnitudes of deformation to perform specific experiments in the lower number of them.
So this is, let's say, we have some kind, when we're doing data correlation, we have modeling error and we have measurement error. Okay, so the measurement error we will always have. And the modeling error, you say, I don't have modeling error because I use directly the data, but as I don't get precisely the points, it means that my modeling error is the distance finally. Okay, something
yes.
like that. And you have used the word. So I say, do we need, in order to use this kind of methods, do we really need actual experiments? Can we see it inversely as a kind of model order reduction scheme? If I have, for instance, a bunch of simulation of whatever car crash with 10 million finite elements, when I have all kinds of material configurations that happen, can we use this kind of methods just to take this great bulk of data and then use to data-driven simple simulation for the next one? Do you think it's possible, or it will be anyway more time consuming than performing actual integration of the constitutive law?
I wouldn't really know. I guess one should have to try to see that.
Because there was a hint which we have a slide 43 where we say, okay, you said that it's some kind of hyper reduction also. So it's maybe when you have small distances in a high number of points, you don't need to make repetitive computation. So maybe you don't really need to see it as a method that directly makes the link between experiments and simulation, but it can also be seen in a more general context. Some kind of
yeah, I understand. To use this as a way to select relevant data, select relevant experiments and numerical simulations.
Yeah, anyway, go further.
General problem
Go further in data analysis.
Yeah, probably, maybe. Yeah. One good example. Maybe we started to a PhD starting here, which is running here, is focusing on the analysis between of the pairing between the mechanical and material states, and doing data analysis on this part to get information out of this distance and pairing between the database and the mechanical solution you retrieve. So that there is also information to get there, and that can be useful.
Yeah, for me, it's always the question of the right the space when you are doing it. Is the space of mechanical quantities always going to be in the stress strain state? But well, some kind of reduced coordinates could be maybe interesting.
But you would have to reformulate the solver to use those coordinates rather than
I don't need to. I can use this coordinate in order to analyze data and to calculate distances. But then I can always, as I know where my reduced coordinates come from, simply it can be just a simple response surface to get back the original quantity.
Sure.
I can always recover because I have labeled all my points with the corresponding stress and deformation tensors. So I can always go back. So I can still keep this. If I keep the reduced coordinate, it means that I'm already doing model order reduction. It's another aspect. It's very rich. Well, I will not like to monopolize the floor, so I will stop here and congratulate once again. And I give back, thank you, Mr. President, and I give you back the floor.
Thank you, Piotr. Now I leave the floor to Professor Michael Ortiz from California Institute of Technology. Do you hear me?
I hear you. Can you hear me?
Okay, great. We hear you.
Hi, Auriane. How are you? Remember me?
Yes.
Okay. So I would like to join your fan club, actually, and say that you've really done a great job. But to me, the main thing is that there seems to be some feedback. Okay. Now it seems to be better.
Okay.
Yeah. The main thing is that the thesis is not the end, and it's just the beginning. Okay. So the fact that you've done such a good job, I think it's an indication that you have a very bright future ahead of you.
Thank you.
And you should make the most of it. I mean, this is not the time slow down, on the contrary, okay?
Mm-hmm.
So anyway, so that's unsolicited advice. So I have some questions and I have some comments, okay? So, and I'll stay within nonlinear elasticity because that's what you've done. Of course, I mean, there are many other questions one would ask about dynamics, about inelasticity, whatever, thermodynamics, but that's unfair, okay? So your work is on nonlinear elasticity, and the question is whether you've made contributions in the area of nonlinear elasticity. Okay, so all my questions and comments are strictly in that area.
Okay.
Okay, so somebody already asked about why models or why data instead of models. Okay, so first of all, do we have anything against models?
I don't.
No, okay. Models are fine. So why don't we just use models? So for instance, take a simple material such as rubber, okay?
Mm-hmm.
And that's simple enough, and that's typical material that is modeled using nonlinear elasticity very often.
Mm-hmm.
Okay, it's a huge business in the tire industry, okay? So how many models of rubber do you think there are? Just rubber elasticity.
A lot of them, and there are
2,
a
3,
new one every year, I guess.
dozens, hundreds.
Yeah.
I just did a Google search under models for, what did I do? Let's see, I have it here. Models for rubber elasticity. No, constitutive models for rubber.
Mm-hmm.
And I got 14 pages with 10 entries in every page, 140 entries. And that's probably just scraping the surface, okay? Mm-hmm. So why do you think there are so many models of rubber?
Because I guess they are not working as fine as one would want for the specific application every time. It's
not so easy, right?
Yeah.
It's fine to say, okay, model, but what model? And how do you know the model is predictive? Of course, you can always use a model and get a lot of garbage very fast. But how do you know it's not garbage? How do you know the models are not predictive? So apparently modeling is not that easy, right?
Mm-hmm.
That would be my conclusion. So
yeah,
after spending 35 years doing constitutive modeling, and this is just nonlinear elasticity. So now I start introducing inelasticity, thermomechanical coupling. Okay, it's not a well-defined problem, right?
Mm-hmm. Sure.
Right. So I think that would be my answer to the question. I mean, it's fine to use models. Give me a good model, please. Please give me a good model. Meaning a model that you can prove it's good, it's predictive, okay? Mm-hmm. And I think anybody can do that. We challenge anyone. So, okay, so I guess so much for models, okay? Anyway, then I have specific questions about things like, for instance, interpolation, okay? So now say you take a typical data set. So now I have to say, actually, I have to brag on behalf of the Afners, okay? So they've used data-driven calculations with billion data point, okay? So in a matter of seconds, okay? So it can actually be done, okay? So why not use interpolation there, okay? So would it be possible to use interpolation of a general data set?
I don't see why it would not be possible, but I don't really see the interest, I think.
Well, so let's say that you say, okay, I want to fill in the gaps in between the points and have a billion data points, and I give you another one, which is none of those billion data points, and I would like to say something about that point. Okay, so could you interpolate a billion data points in dimension 12?
You could, but not at zero computational cost.
How?
You could think of manifold reconstruction.
No. Talking about interpolation. Okay.
That's some form of
not data reduction. So would you use simplicial elements in dimension 12?
Oh, you could do that, but yeah, interpolation really on the fly. You mean? Yeah, simplicial interpolation is one way to go, because I know you've been using that.
No, we did that with Klusemann, but with structured data. Okay,
yes.
So data that wasn't agreed. This is completely unstructured data. Okay. Can you interpolate the data in any easy way by meshing the data?
You would have to, mesh the phase space, maybe use some kind of Voronoi tessellation.
Come on, can anyone mesh in dimension 12?
No, I don't know.
No, the answer is no. Okay,
no, okay.
But you could use interpolation in a mesh-free way, right? Do you mesh-free interpolation? So again, you have a whole bunch of points. You have another point which is neither, and you want to interpolate some function there. What would be a mesh-free interpolation method that you could use in dimension 12?
Splines.
No.
No, I mean not splines in 2 dimension, but high dimension.
Try again. Have you heard about Max-Dent interpolation?
Yes.
That's mesh-free, right? So in principle, you could use it in dimension 12 with any number of points, because you need to know nearest neighbors.
I didn't see that.
It's always about determining nearest neighbors. But once you know the nearest neighbors, you could use Max-Dent to interpolate, and that minimizes that function. Does that sound familiar in any way?
Yes, sure. But I never thought of it as well. I didn't see where you were coming.
Well, so it's been done, right? It's been done by
right?
It's been done by Kirchhofer and somebody else in a paper called data-driven methods for noisy data sets. That's basically what was done, was interpolate the data set using maximum entropy interpolation, okay, which is mesh-free, and then you can do it, and so in principle, interpolation can be done.
Yes, okay. It's interpolation. But never saw it that way.
Yeah, okay, so there was a question and a comment.
Yes.
Okay, so I was going to ask about incremental Lagrangian, so updated Lagrangian methods. And okay, I'm sorry, I think there is somebody who has the microphone open and is putting a lot of noise into the calculation, into the
I can switch conversation. My microphone once.
Or maybe it's just feedback from me.
Okay. Yes, I think it is.
It is feedback from me. Okay, so is there any way you can remove the feedback? I'm annoying myself.
Is it better this way when I switch off my microphone?
Maybe, yeah. Okay, let's try. Have you given any thought about the possibility of doing data-driven updated Lagrangian calculations? Which would be another way of doing finite elasticity, right? And this is really a question. I don't know the answer to this, so.
I haven't thought about it and haven't tried.
Would it be practical? I guess you would need data sets for incremental strains and for shear stresses given the reference state, right? So you would have to have a collection of data sets for incremental states at different reference states, right? So that's probably not very practical, right? I would say.
Yeah, and you would think of doing the same thing as what has been done in incremental inelasticity, where you have this moving data sets for each increment or something.
Something like that. Have you thought about that at all?
No, I haven't.
No. I mean, it seems to me rather impractical, right? Because then you really multiply the dimension
I think so.
Data set by 2, right? You need the reference state, and then you need all possible increments from there. So,
and I don't really see the interest here, at least in just finite elasticity.
okay, then let's go to the debate of PF versus SE. Okay. Lagrangian versus how do you call them? Lagrangian versus material?
Yeah, nominal.
Nominal. Yeah, okay. Why do you think mathematicians don't like the SE approach? That's what you call Lagrangian, right? Hello, are you there?
Yes, I was just getting the right slides. Because of this, the nonlinearity in the compatibility and the nonlinearity in the stress equilibrium, which should no longer have here, and that's why they managed to
So it's
get...
not that mathematicians are difficult, which they
Yeah.
are. It's that they would like to show that in fact there is a solution, and there is no way you can prove anything with SE. In fact, you can easily find counterexamples, because what happens with a distance function? So what happens with a distance function if you formulate it in terms of S and E? Is it a nice function?
But well, it's here we use the quadratic function
Or S and E?
Or S and E.
And is that a nice function?
It's a Savant-like distance, and it may cause problems. But we haven't gotten...
What problems? What problems does it cause?
At very small strains, you could have similar small strains with very dissimilar stresses. So
the distance function is not, say, anything like quadratic, right? So in fact, the distance function is not even convex, like the Saint-Venant-Kirchhoff model, right? So you could have instabilities, you could have wrinkling, you could have cavitation, and your distance function would not control that, right?
Yes.
You agree?
I agree in principle, but I haven't...
So it's a very, very bad distance function. Of course, I mean, if the strains are reasonably small, then nothing will happen, right? But if you want to prove something, you cannot discard strain concentration somewhere that will induce local instabilities, right? I mean, another way of saying that is that if you take that distance function, okay, and you compute the second derivative, it's not going to be positive definite. Okay, because of it's going to have a geometric stiffness term that is not doesn't have a defined sign. Okay, so it is. I mean, it looks very good. We engineers like very much SNE. It's like it's addictive. Okay, so a little bit like a drug. But when you try to do the math, it's really horrible. I mean, it's really very, very bad stuff. So that's why mathematicians don't touch SNE. They do everything in terms of PNF, because then P and F are in linear spaces, and the distance function could be something like quadratic, for instance. Do you know of any problem of that formulation, P and F?
Apart from the fact that you have to enforce this conservation of angular momentum.
Apart from that, what happens to the determinant, for instance? Is there any problem? So you said that the determinant of that has to be greater than 0.
Yes. But that was for generating databases.
Right. So if you're doing distance minimization in PNF, is that something you can guarantee in general, that the determinant will be greater than 0? For
the mechanical solution, you mean?
Yes.
I don't know.
Yeah. So that's the problem, that you really have no control on the determinant. So the PNF formulation also has troubles of its own. And that's why nonlinear elasticity is in a completely open field in mathematics. Okay, so if you can prove something, then the formulation is not physical. If you make the formulation physical, then you cannot prove anything. So it's it's a very tough business.
Okay.
Anyway, so that's both a question and a comment. But then I think Professor Reze spoke about material frame indifference and isotropy, okay? So how do you build material frame indifference and isotropy into a data-driven formulation?
For material frame indifference, well, in the ES formulation, it's encoded in itself. In the FNP formulation, you can think of adding orbits to the database, or either in the database in a sort of pre-computing stage, or included in the distance, adding a minimization to the rotational tensor.
Yeah, exactly. So you have to think of data points not as points, but entire orbits by SL3. Basically, so you have an F in the data set, and R times F is also in the data set for any rotation R, right?
Yes.
So that's the way it fits. So then the data, of course, has to be material frame indifferent, the data. How about isotropy?
Isotropy, you can get the invariance out of the data and work with a invariant-based distance.
But those are also orbits, right? I mean, if you have material,
but different ones.
Yes, if the material is isotropic and F is in the data set, then R times F, so with R on the other side, also has to be in the data set, right? So now this would be orbits by the symmetry group. And so it's whatever the material wants to do, right? I mean, it's only the material data set, because the conservation laws are there just to guarantee equilibrium and compatibility, right? The material can do anything it wants, right?
Sure.
So there was also a question, a leading question and a comment. I'm answering all my questions, I'm sorry. It comes with age. No, but then I want to say something about execution. No, I want to ask something about execution time. You're doing no linear elasticity, right?
Yes.
Okay. Are you doing Newton-Raphson?
Yes.
No, come on. You're not doing Newton-Raphson. You're doing you're not doing the
inside the computation of the mechanical states, you have a nonlinear system to solve, and there Newton-Raphson. But sure, you're not doing Newton-Raphson on the whole structure like in classical finite elements.
Yes, I'm sorry. I was thinking of P and F where the constraints are linear.
Oh yeah, sure.
Yeah, I'm sorry. I was thinking of that specifically. So if you continue with that, okay, the constraints are linear, so you have linear problems to solve, right?
If you don't have the conservation of angular momentum, yeah.
Right. So you think that, again, the conservation of angular momentum is in the data set. So of course, there are pros and cons, and we have discussed those very extensively, but assume that the data set also satisfies angular momentum. Okay? So then you're just doing linear problems. But where is the main cost?
Well, it would be in the search in the database, the main cost.
But
it's easily breakable.
So the way to accelerate the calculations is to have very fast searches, right?
Yes.
Wouldn't you say?
Yeah, sure.
Yeah, which is a huge field actually, and so again, as a comment, so Robert Eggersman, from Aachen, so they has been looking at this and has done wonderful work and found searching algorithms that can really search through billion point data sets in a matter of seconds. Okay, so that would probably be the thing that you would focus on to accelerate the calculations, right?
Yes, but maybe a comment on that is that when I used not billion, but up to 25 million points, and I was just limited by the memory of my laptop, actually, not really the to generate the points themselves. And really I know you wouldn't agree, but the standard tree-based algorithm, at least in 2D, is already good enough to search within this 25 points within seconds. I mean.
Yep. Apparently, you can do better than that. That's
yeah, sure.
So it's
I can imagine, and I'm starting to look into what he did, but
talk to Robert.
yes,
he's a nice guy.
I know.
And so finally, okay, yeah, the FE squared is, I think, the thing that I knew the least about. So am I right in saying that it's been done for small strains or not?
In my work, you mean?
Yes,
Yes, only for small strains.
Yeah.
Because I did that in the, well, last part of my my work, and but I have begun to take it to finite strains, but I haven't had any good results to show yet. So.
So if you were to extend it to finite deformations, do you anticipate any problems with FE squared? Does it work? FE squared for large strains?
Yes. I mean, regular FE squared, you need to have this this tangent operator, which is even maybe harder. But in let me get the next slide. Yeah, here. I mean, you can write this slide with exactly the same structure, but just replace epsilon and sigma with ENS or FNP. That would be the same. And why not?
It's a completely different business. So, for instance, imagine that you have in that figure that you have on the right, instead of a circular inclusion, you have, for instance, fibers, okay, and you compress the fibers. What could happen to the fibers?
Yeah, the buckling, or
they could buckle. So that means that the effective behavior of the unit cell is stable or unstable?
Yeah, unstable.
It's unstable.
Unstable. Yeah.
So that means that homogenization doesn't work in this way in finite strains for all these reasons. And there's a theorem though by Brides and Müller that shows that to do homogenization in finite strains, you have to consider multiple cells. Okay, so not just one cell, but then 2 by 2, then 3 by 3, then 4 by 4, then 5 by 5. So you can account for these local instabilities. And in fact, to get the exact behavior, you have to consider an infinite number of cells. Okay, otherwise you don't get the right behavior. So this is not just a matter of degree. I mean, it's a completely different business going from small strains to large deformations. Yeah, but
these difficulties, they don't have anything to do with the data driven setting. They're intrinsic to the finite strain homogenization. Yeah,
I agree. I'm just issuing a warning that it's not just going from small strains to finite strains. That's good. No, it's a different. I mean, if you want to do it right, it's a different business altogether.
Okay. Sure.
Okay. I'll relent now, and I'll give it back to the chair.
Thank you.
Thank you, Professor Ortiz. So I guess it's my turn to ask questions. Can you go back to page 13 about the distance? And I guess that if you have only one material state at 0, 0 in the space D, you can start the simulation. Is that right?
You can, or you can't. Yeah.
Are you able to start the simulation with only one material state?
You can.
So the results totally depends on the matrix C. Are you right? Are you okay with that?
Yes.
Okay, and do you think that there is an optimal choice of this tensor, or is it an issue or not?
Yes, sure. We haven't explored that really in my work, but the value of C is actually if you have a finite number of points in the database, it has a huge impact. on the mechanical response. So obviously this value can be optimized for the current problem and the current database that you have, and it should be probably.
So I guess here it's isotropic tensor in your simulation, or?
Actually, for ENS formulation, it's an isotropic tensor, yes. But here it's really it's a scalar. C is
okay.
So there is no.
And what if you have incompressible materials for linear strain? In case of linear strain, small strain, do you have to change the definition of the distance, or do you propose something else for incompressible materials?
I would say you do as in finite strain. You encode it in the database, but you.
Yeah, I agree. It should be already in the database if
yes.
the material is incompressible. But do you need to change the definition of the distance, or?
Not the definition. You could use a value of C that resembles a incompressible material stiffness, elastic stiffness, where you have incompressibility of a Poisson's ratio of 0.5. But you could also perform the simulation without this knowledge. And if the modulus of C is good enough, you should obtain good enough results, I think. If it's encoded in the database, it just changes the way you search in the database.
Yeah, but I guess that the inverse of the tensor C appears in your definition of the distance. So in case of incompressibility, are you sure you can write things like that? Or?
Yes, I was thinking maybe in plane stress where it is defined, but in 3D, I don't know.
Okay, great. Very interesting. Your talk was very interesting and clear. So I have many questions, but I need to select. And on your page 43, about the FE square.
Yes.
Did you use the tree-based algorithm to select the material points in that situation?
To search in the database?
Yeah,
yes.
yeah.
Yes, sure.
Do you think it's a crucial contribution to the efficiency of the method for the FE square? What if you cancel this algorithm? Did you try that?
I haven't tried. But sure, if your data-driven simulations use a linear search, they're going to be much more costly.
Yeah. Mm-hmm. And I think it's a crucial point that
sure.
tree-based algorithm. It's very interesting. Okay. And another question, what if you rotate your mesh for large strain? Maybe in case of large strain, your distance is defined by F and P formulation. Mm-hmm. And what if you rotate your mesh? Will you have exactly the same algorithm or not?
You have the same algorithm, but the database that you generated is no longer really. I mean, it depends on how you generated it, but maybe something I kind of I didn't mention is that I generate the database in the same frame as the one I use for the mesh. Okay. And obviously, you will need points in this direction, or you can use what we discussed with Michael to add the orbit of the points, and then you no longer really care for the orientation of your mesh with respect to the orientation of the database.
Okay, great. Oh, that was my last question. Congratulations. Thank you very much for your answers.